Hello AP Chemistry and welcome to section 14.6 covering reaction mechanisms. So, when we write a reaction, like this for example, this is our overall reaction. That's not actually a picture of what happens inside, right? So I know we talked about, for example, back in chapters 6 through 9, I believe, right? We talked about how when we calculate the enthalpy of a reaction, we can think about it, right, as breaking all these bonds and making all these bonds, right? But all that actually gives us, right, if we think about a graph, right, is that just gives us this part here, right? That gives us the change in energy. That doesn't tell us all that information, right, that happens up here, right? So going back to that other graph, right, it doesn't tell us what the transition state looks like. It doesn't tell us what happens on the way up here, right, as we go over here, right? This is all just a big gray area, right? Reaction mechanisms fill that part in for us. So reaction mechanisms are always experimentally determined, okay? And they're sort of the exact steps that happen in order to go from reactant to product as best as the science will let us figure it out. All right. So for this reaction, as best as it is understood right now, we know that what actually happens is that there are two steps, right? In step 1, an NO2 actually collides with an NO2, right, producing NO3 and NO, right? Subsequently, that NO3 then reacts with a CO, right? So these two collide, all right, producing an NO2 and a CO2, right? When we sum these two reactions, we get the overall reaction, right? Meaning that we get, right, or if we just were to sum it up literally, right, we have 2 NO2, right, plus an NO3 plus a CO, and that gives us an NO3, an NO, an NO2, and a CO2. Okay. Now, if we think about our reaction up here, right, this is a reactant, right? And, well, anyway, if we look here and we cancel out the things that cancel, right, we see that there's one NO2 here because one is produced, right, versus 2 being consumed, which means net, right, 1 is consumed. Okay. We see that we have a CO here, right? We see that there's an NO3 here and an NO3 here, right, meaning 1 is consumed and 1 is produced, which means it doesn't show up in the net process, right? And then on my product side, we have our NO and we have our CO2. So in terms of terminology, okay, note that NO2, it is like both consumed and then produced, right? So it's not labeled as an intermediate. An intermediate, by definition, has to be something that is produced and then subsequently consumed, such that it does not show up in your overall reaction. Okay, so if we were asked about intermediates, NO3 would be our intermediate because it's produced, subsequently consumed, therefore does not show up in my overall reaction. Okay, so what we would say is that this reaction actually occurs via these two elementary steps. Okay, step 1 and step 2. Right? We would say that this step is bimolecular, this step is bimolecular, and if we were going to write rate laws for step 1, right? So for step 1, if we were going to write a rate law, it is based on just the molecularity, right? So we would say that the rate is equal to K1, right? I'm symbolizing step 1, times NO2 raised to the first power, NO2 raised to the first power, right? So then we could also simplify this as K1 NO2 squared. Okay, and that would be the rate law because it's an elementary step, right? We could not do that for this reaction though, right? Because that's not an elementary step, right? That's an overall reaction. Okay, on a graph, what does that mean, right? So here we still have reactants versus my product, right? So this is still my overall delta E for the process, okay? But we understand again that this is a two-step process, right? And we know that because we have one activation energy and a second activation energy with an intermediate in the middle, right? Meaning something comes out and then we then use that something else, okay? Which means that so we have one activation energy produce the intermediate, another activation energy, and then we reach our products, okay? If it were a three-step mechanism, right, there would be a third hump over there. Yeah, make sense? Okay. So a little bit of thinking about this. So consider this reaction. Write the rate law assuming it involves a single elementary reaction, which means that if we assume this is a single elementary step, it's based on its molecularity, which means that my rate law would simply say rate is equal to K times NO squared times Br2 to the first power, right? Is a single step mechanism likely? No, this is a termolecular process. It's saying that three molecules have to run into each other with the right amount of energy, with the right orientation, which is virtually impossible. So, no, not possible. Not likely. It's not impossible, just not likely. So ozone reacts with nitrogen dioxide to produce dinitrogen pentoxide and oxygen. The reaction is believed to occur in 2 steps. Okay? So it's telling you that these are the steps of the mechanism, right? Oh my gosh. So it says that these are basically our elementary steps. So the experimental rate law is this. What can you say about the relative rates of the two-step mechanism? So we know that the rate law is always going to be based on the rate determining step, which is also our slow step. Meaning that whatever step is the slowest, right, that's going to have an impact on my rate, right? A bigger impact on my rate than any other step, right? So if I look here, this says that my rate law involves the ozone and NO2, right? If I look here, oh, ozone and NO2 both show up in this rate, or this step, right? Which means that this must be our, ding, 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 right, this is our rate determining step, this is our slow step, and this would be our relatively fast step. Yes? Does that make sense? Okay, thank you very much, be good, and I will see you soon. Bye.